Okay, so far we have found that if any uh, lossless transmission line is terminated by any arbitrary load ZL, then total voltage and total current, they are mathematically represented by these equations. So V as a function of that Z is represented as V naught plus e power minus j beta Z, which is representing a forward wave, and V naught minus e plus j beta Z, which is representing backward wave. So on this transmission line, as we have discussed before, there will be one wave traveling in this direction, and after reflection from this point, there may be some backward wave or reflected wave traveling in the negative z direction. And the current at any point as a function of z is represented as 1 over z naught v naught plus e power minus j beta z, which is representing the forward current wave, and v naught minus divided by z naught e plus j beta z, representing the backward current wave. And then we also represented these two equations in terms of a parameter that we defined as reflection coefficient, represented by this symbol gamma, and we define it as v naught minus by v naught plus, which is the reflection coefficient at the load position. Okay, so at this position, how much part of the wave will be reflected? It is represented as the magnitude of the reflected wave, that is v naught minus, divided by the magnitude of the incident wave, which is v naught plus. So in terms of reflection coefficient, these two equations can also be represented in this manner. So voltage v of z can also be represented in this form, that is v naught plus e minus j beta z plus reflection coefficient e plus j beta z. And current wave can be represented as v naught plus divided by z naught e power minus j beta z minus reflection coefficient e plus j beta z. So what we have done is this v naught minus is reflection coefficient multiplied with v naught plus. So what I have done is, in place of v naught minus over here and in place of v naught minus, I have used this term, and as a result we got alternate representations for total voltage and total current at any point on this transmission line. So this is alternate form. Now once we know the current and voltage mathematical form as a function of z, so we can use them at any position. So let's assume that I want to find out how much is the impedance at this point. Okay, so because with respect to this figure, it is the input of our circuit. So I will represent that whatever is the impedance at this point, I will call it Zn. Okay, now our goal is to find out the expression for Zin. Now, in terms of coordinate axis, that is z, this position is defined as z is equal to minus L, because we assumed that this transmission line may have some length, let's say L. So at this point, z is equal to minus L. So how much will be impedance at this point? So we will find out how much is the voltage between these 2 points and then divide it by how much is the current at that point. So we have the expressions of, I'm going to use the alternate forms. So if I want to find out Z in, I will substitute V at Z is equal to minus L divided by current at Z equal to minus L. So all you need to do is replace Z over here by minus L and similarly Z over here by minus L. So let me go through uh, some of the steps so that it become easier for you to solve it yourself in a step-by-step manner. So Z in will be equal to V naught plus and E plus J beta L plus reflection coefficient E power minus J beta L. This is going to be the expression of V of minus L, and then we will divide it by I of minus L. So it will be V naught plus divided by Z naught E plus J beta L minus reflection coefficient E power minus J beta L. Now this V naught plus will cancel out. So, and then I will bring this Z naught into the numerator. So what you will get is Z in will come out to be equal to Z naught E plus J beta L plus reflection coefficient E power minus J beta L divided by E plus J beta L minus reflection coefficient E power minus J beta L. This expression can be further simplified by taking this factor as common from the numerator as well as e raised to power j beta as common from the denominator. So whatever term you take out as common in the numerator and denominator, because it's the same term, so it will cancel out. So what you will get is Z in will be equal to Z naught. And what will be left inside the bracket? So you will get 1 over here because we have taken this as common plus reflection coefficient, and this will become e power minus j 2 beta. And similarly in the denominator, we get 1 minus reflection coefficient e power minus j 2 beta. Now this expression is known as transmission line impedance equation. Transmission line in impedance equation. So basically, with the help of this equation, we will be able to find out impedance at any point on the transmission line. All we need to know, all we need to identify is what is the position at we are finding L, at we are finding Z. So you can clearly see that this Zn will depend upon L. So with respect to this figure, L means whether I'm interested in finding impedance at this point. So you will put this value of L. If I'm interested in finding out how much is the impedance at this point, so you need to find out how much is this L. So once you know this L, you will be able to find out the impedance. So if uh, if I want to find out impedance at this point, okay, right at the position of the load, so you can clearly see over here L will be equal to 0. So you can also find ZL with the help of this equation, even though we are representing it as Z in. So that doesn't mean that only this is input impedance. The reason I'm calling it as input impedance is because of the general structure of the circuit, that you will have a load, and then you will have some transmission line with some length, and then maybe we will be interested in finding out how much is the impedance at this point. So this point is input, but what I'm saying is, even if you find Z in at this position, so then it's still it means that L is 0. So it means you haven't connected any load. So it means this position will become your input. So it means even though it is Z in, but from this equation, Z in will come out to be equal to ZL. Okay. Now there is one alternate uh, representation of this transmission line in impedance equation, and that we can easily derive by replacing gamma by its value in terms of impedance. So in our previous lecture, we have found that this reflection coefficient, which is at this position, it can be calculated with the help of this equation, that is ZL minus Z naught divided by ZL plus Z naught. Okay, we have already covered this thing. So in this expression, if you replace gamma by this, and then of course you have to take you have to do some steps by taking this expression as LCM in the numerator and denominator. So uh, finally you will get this expression. So what you need to do after you will get this expression. Of course you have to perform 2 or 3 steps, which I'm not doing over here, because of the reason that this is simple, straightforward substitution and rearrangement. There is nothing complicated and anything. It has nothing to do with the concepts of microwave engineering. So that's why I'm not spending much time on this. So let me write down the expression that you will get. So this is another form of transmission line impedance equation. Now you can practice and try to get this expression, but let me point out uh, that in this expression you can't see any tangent function. Okay, so when you replace gamma by this, so from where you will get this tangent function, which is in the final expression. So in this original expression, you have e power minus j2 beta L as well as in the denominator. And we know from Euler's relationship that exponential function e plus j theta or e power minus j theta, it can always be represented as cos theta minus plus j sine theta. So in order to derive this expression, you also need to replace this exponential function in terms of sine and cosine. And then what you need to do is in order to get tangent function, what you will be doing is you will be dividing this by cos theta. So you will get 1 minus plus tangent theta. So why you get tangent function over here is by making use of Euler's relation. So depending upon what information is given to you in the question, you can either use this equation to find impedance, or you can use this expression to find impedance. So if reflection coefficient is given to you, then you can use this expression. But if reflection coefficient is not given but ZL is given to you, then it makes sense to use this expression to find impedance. But whether you use this expression or you use this expression, the final result will be the same, because of the reason that reflection coefficient and ZL, they are related to one another using this expression. Okay. Now let's talk about some special cases of terminated lines. Special cases of lossless terminated lines. So in the first case, I will talk about special lengths. Special lengths. Or let me first discuss special loads before talking about special lengths. So the transmission line that we are discussing, in our previous discussion, we assumed that there is a general load which is connected to this transmission line. Okay. But now we will consider some special loads. And these special loads will help you to further understand the theory of transmission line. Okay. So the first special load that we can talk about is short circuit load. Short circuit load, which means that ZL is equal to 0. Which means that you connect these two ends together directly. So ZL will be equal to 0. So you terminated a transmission line with a short circuit load. Now let's find out what will happen to the mathematical description of this circuit. Okay, so first of all, we need to find out how much is going to be the reflection at this point. So when signal is coming from the source side, when it arrives at this point, so how much is going to be reflection? So we already derive that reflection coefficient at load position is simply ZL minus Z0 ZL plus Z0. Now ZL is equal to 0. And then Z0 with Z0 will cancel out. So reflection coefficient becomes equal to -1. Reflection coefficient becomes equal to -1. Now reflection coefficient is generally complex number. So we can interpret this result as reflection coefficient magnitude is equal to 1. And phase of the reflection coefficient is 180 degree or pi radian, which means that signal coming from the source side, when it arrives at this point, the whole signal will be reflected because the magnitude is 1 and phase is 180 degree, which means that the reflected signal phase will be 180 degree as compared to the incident signal. Okay. So this is the first effect of connecting a short circuit load to any circuit or any transmission line, that reflection coefficient will become -1. And if you remember regarding the impedance matching issue, so it means that this is representing a totally mismatch case because nothing is delivered to the load, everything is reflected back. Similarly, what will happen to the voltages and currents along this transmission line? So we can make use of this result into the original expression of total voltages and current. So total voltage, which was uh, represented in this manner, the alternate forms. So this is equal to -1. So we get V naught plus e power minus j beta z minus e plus j beta z. This result, again, we can make use of Euler's relationship. So this result, after making use of Euler's relationship, it will become equal to minus j 2v naught plus sine beta z. So this is the behavior of the voltage along a short circuit transmission line. I will plot this equation graphically, and then we will talk about its significance. Okay. Similarly, the current on this short circuited transmission line, it can be represented in general form like this. And now, because we know the value of reflection coefficient is -1, so it will become plus. And again, by making use of Euler's relationship, it will become 2 times V naught plus Z naught cos beta Z. So one thing that you can clearly observe is the voltage, it will be varying as a sine function, whereas the current will be varying as cosine function. Okay, so let me try to plot these two results, and then it will be easier for us to comment on the behavior. So this is the point at which we have connected the load. So this is Z equal to 0. Okay, the point at which we are connecting load is Z equal to 0, and then we move towards the load. Sorry, then we move toward this generator. So Z will become, it will no longer be 0. But let's find out what is the behavior at that point, and then the behavior at any other point. Okay, so at Z equal to 0, what will be the voltage? So let's assume that first I'm plotting the voltage. So let's assume this is the voltage. So voltage at Z equal to 0. So Z equal to 0 means sine of 0 is 0. So it means voltage is equal to 0 at 1. And then as you increase that, the voltage will increase as per sine function. Okay, and then it will attain its maximum value somewhere over here, and we can easily find out what is that Z value at which the voltage will become maximum. Okay, so when this voltage will become maximum, when this function sine attain its maximum value. Okay, so let me do some rough calculations over here. Sine beta Z. So we already know that this beta is related to lambda. So in place of beta, we can write 2 pi by lambda, and then Z. Okay, so when sine function will attain its maximum value, we know that sine becomes maximum at pi by 2. So what should be Z so that you get pi by 2 over here? So it's obvious that Z has to be equal to lambda by 4. So if you put Z equal to lambda by 4, what will happen? Lambda will cancel out, this 2 will cancel out. So you will end up with sine pi by 2, which is equal to 1. So now I can also point out that this is lambda by 4. At distance lambda by 4, the voltage will become maximum. And then this voltage will again become 0. And you can use this result, and it is easier for you now to point out that when this voltage will again be zero, it will be equal to lambda by 2. So first voltage is zero at z equal to zero, then it attains its maximum value, then it again becomes zero, and then it will be the well-known sine function repeating itself. Okay, so this is 3 lambda by 4, and this is lambda. So after lambda, the voltage will cover its complete cycle. So now this is telling us that if voltage at this point is zero, and it makes sense why voltage at this point is zero, because we have connected a short circuit load, and the voltage across short circuit load is zero. Okay, and then when you move a distance of lambda by 4, so if you are standing at some distance which is lambda by 4 from this short circuit load, at this point if you measure the voltage, it will be maximum. Okay, so this is maximum. And then if you further move, and if your distance from this position is lambda by 2, again the voltage will be zero. So now I hope this all makes sense. And now you can also find out the graphical representation for current. Current is varying as cosine function. So when z is equal to 0, cos 0 and cos of 0 will be maximum. So it means at z equal to 0, the current will be maximum. And again, for short circuit load, it makes sense. We all know, even from our circuit theory, that across the short circuit load, voltage is zero, but current is maximum. Okay, so this is a maximum current. And then if you move a distance of lambda by 4, the current will become minimum. So this is lambda by 4. And again, as cosine function behavior is easy to follow, so you will get something like this. Okay. So what is the main point that you can see over here is, let me point it out, this is lambda by 2. Okay. So what behavior you can see? When voltage is minimum, current is maximum. When voltage is maximum, current is minimum. And then this is repeating itself. But there is a 90-degree phase difference between voltages and current, and which makes sense because voltage is cosine function and current is behaving as voltage is behaving in terms of sine function and current is behaving as cosine function, and we already know that sine and cosine, they have a 90-degree phase difference, and this behavior is being reflected in the behavior of current and voltages. Okay. Now this is the behavior of voltages and currents for this special load. Similarly, I can also find out how much will be the input impedance. So if I want to find out impedance at this circuit, so when you connect a transmission line with a short circuit load, how much will be the input impedance? Now, input impedance equation, we can, as I mentioned, you can either make use of this equation or you can make use of this. Let me use equation number 2. So if you put ZL equal to 0, if you put ZL equal to 0 in this original expression, and it is very straightforward equation, so just replace ZL by 0 and then find out what you will get. So I am using this result directly. So you will find out that Zn will be equal to J Z naught tangent beta L. So from where you will get this expression? With using this one. So ZL is equal to 0, ZL equal to 0. So this Z naught and Z naught will cancel out. So you will be only left with this term, ZJ naught, JZ naught tangent beta. So now this is another interesting behavior of short circuit terminated line, that the input impedance is, first of all, it's purely imaginary. If you connect a short circuit load to any transmission line and then you find out the impedance at any point, that impedance is behaving as purely imaginary one. Okay, so this is the first thing. And then the other thing that we can see is that this impedance, it is varying in terms of tangent function, Okay, now if I plot this equation somewhere over here, let me remove this. And so which equation I want to plot now? I want to plot Zn is equal to J Z naught tangent beta L. Okay, so let me plot it over here. Now, in this equation, we have L, but you already know that uh, this axis is Z, but the actual, when you move along this direction, so actually L is changing. Okay, and we already know the relationship that Z is equal to minus L. Okay, so at this position, you can say L is equal to 0. And then when you move away, so L is increasing. So Z equal to 0 or L equal to 0 is the same thing. So when L is equal to 0, it means we are right at this point. So L is equal to 0 means tangent 0, and tangent 0, it means 0. So at this point, impedance, so this is now Z in. So at this point, impedance will be 0. And then as you move away, or in other words, as L increases, so tangent function will increase. So this function will start increasing. Okay, and you will find out that as soon as Z or L become equal to lambda by 4, tangent becomes 90. So tangent 90 is infinity. So impedance becomes infinite. At which point? At lambda by 4. And then what will happen after lambda by 4? So we know that after, if you put tangent 91 or 92, so the function will no longer be infinite. So after lambda by 4, it will start decreasing again. So from, it will be, of course, plus infinity, and then it will become minus infinity, and then it will start decreasing like this. Okay. At which point will be equal to 0? It will be equal to lambda by 2. And after that, it will repeat itself in the same manner. Again, it will be like this. So again, I'm not uh, drawing a very accurate graph, but the main point that you need to understand is at this point where you have connected a short circuit load, impedance is equal to 0, and it makes sense. And if I find the impedance at this point, so of course we have connected a short circuit load. So at this point, impedance must be equal to 0. But the interesting result is if you move from this point and a distance of lambda by 4 and you measure the impedance will no longer be 0, it will be infinity. And impedance equal to infinity means that you will get an open circuit behavior. So from this figure, this is your short circuit point. And then this point is open circuit. But again, you can see this open circuit and short circuit behavior is repeating itself. At this point, again 0, at this point again infinity, and again, so this pattern will repeat itself. And from this we get the important result, which I'm going to write over here, is transmission line is a periodic structure. It repeats its behavior after every lambda by 2. And this thing is reflected over here. If you go back, when I was plotting voltage. At this point, voltage is 0. So after how much distance, the voltage is also is again 0, this point. And how much is this distance? Lambda by 2. Okay. Similarly, current is maximum over here. After how much distance, you get the same behavior again. If you see, you get the same behavior at lambda by 2. Okay. So now this is the important concept that we will be using throughout this course, and that is transmission line is a periodic structure. It repeats its behavior after every lambda by 2 distance. Okay. Now let's move on to the second special load. So first I consider short circuit load. Now I'm going to consider a second special load, and that is open circuit load. And open circuit load means ZL is equal to infinity. So now the same transmission line at this position, you are not connecting anything. So it means you left the two ends of your transmission line open. So this is open circuit termination. Now let's see what will be the behavior of this transmission line. So first of all, I will find out how much is going to be the reflection coefficient if you connect a transmission line with an open circuit load. So making use of this standard equation to find the reflection coefficient at the load point, you will find out that this comes out to be equal to +1 for ZL equal to infinity. Of course, in this case, if you directly put ZL is equal to infinity and divide it by infinity, so infinity by infinity is not equal to, you cannot say it's directly equal to +1. You have to make use of one of the rule that you might have studied in some previous maths courses. It's, I think, something called L'Hopital rule. So make use of that, and you will find out that infinity by infinity is equal to +1. So what does that mean? It means that the magnitude of the reflection coefficient is 1 and the phase of the reflection coefficient is 0. So that is something that you need to see, that the difference of short circuit and open circuit load. We get this behavior, and now we are getting different behavior. What is the difference? Difference is, again, this is undesirable situation because any signal coming from the source side, all of it will be reflected because the magnitude of reflection coefficient is 1. But now phase is equal to 0. It means the reflected signal, its phase will be the same as that of the incident signal. Okay. So now the phase is not changed by 180 degree as it was changed in the case of short circuit load. Let's see its effect on the voltages and current equation. So let me use this one. So this is the original expression of the voltage. Now in this case, reflection coefficient is not -1, you get +1. So now you have plus something. So again, making use of the Euler's relationship, the voltage will be function of cosine now, not sine. Okay, so this is something that you can easily do on your own. So what I'm going to do is I'm going to write down that voltage will be equal to 2V naught cos beta z. And similarly, if you use this value of reflection coefficient equal to +1 in the current expression, so now this will remain -1. Okay, so when you have minus exponential function, that is the difference of these two exponential function, then you will get sine. So now for this case, current will be in terms of sine. Okay, and you can also find out input impedance. Okay, if ZL is equal to infinity, how much will be Zn? So going back to this equation that I'm talking about, put ZL equal to infinity, ZL equal to infinity. So again, If you directly substitute ZL equal to infinity, so you might come across infinity by infinity. So make sure that you resolve this uncertainty of infinity by infinity by you making use of L'Hopital rule. And in this case, you will find out that Zn will be equal to minus Jz naught cotangent beta L. So now this is going to be the result for open circuit load. Again, what is the main point that you need to look at is the behavior of impedance. Again, impedance becomes purely imaginary. So if transmission line is terminated by open circuit load, impedance at any point, it will be purely imaginary. And the other thing that you can see is how much is impedance at any position. It will depend on L, and you can see it is now as cotangent function. Now, what is going to be the difference as compared to the previous case? Now voltage is varying as cosine function and current is varying as sine function. So the previous graphs that I was plotting, this was for voltage. Now this graph will be for current, because at z equal to 0, what will happen? At z equal to 0, sine of 0, so it is 0, so current will be now 0. And at z equal to 0, voltage will be maximum. So at z equal to 0, voltage will be maximum. So now this graph will be for voltage. So the behavior of current and voltage has become totally changed. At the load position, now current is. Now again, if you relate this to the circuit theory, it makes sense, because when you connect open circuit load, no current can flow through open circuit. So at z equal to 0, current is 0. But we know from circuit theory that the voltage across open circuit load is maximum. And this is what you can see: at z equal to 0, voltage is maximum. Similarly, this graph, which was for Zn, now we have to change this, because at z equal to 0, impedance is no longer 0, because now it is function of cotangent. So rather than having, when you put L equal to 0, so cotangent 0 will become infinity. Okay, so I'm just going to plot only Zn because its behavior is different. So at this point where L is equal to 0, and as I was telling, Z equal to 0 is 1 and the same thing, you will get a maximum. So let's consider that you get minus, because this is minus something. So minus infinity. So volt impedance will be infinite. But as L increases, so now L is increasing. As L increases, the impedance will vary and it will become 0. How, at which point it will become 0? It will become 0 at lambda by 4. And then after lambda by 4, it will again start increasing and it will again becomes maximum at lambda by 2. So you can see the periodic nature. At this point, impedance is maximum, and again you get maximum at lambda by 2. Okay. But you can also relate this, that at this point you have connected an open circuit load. But if you move a distance of lambda by 4 from your open circuit load, the impedance is 0, which means it is a short circuit point. So it means at this point, if you measure the impedance, it is infinity, open circuit. But if you move to some point, let's say somewhere over here, and if this distance is lambda by 4, and then if you measure impedance over here, you will find out that impedance is 0, which means it is a short circuit load. So, and then it will repeat itself. If you further move, let's say lambda by 4, or if this distance is equal to lambda by 2, so if this is infinity, this point will also be infinity because of the periodic nature. So again, this statement is a general statement. You will always get repetition of behavior after lambda by 2. So voltages, currents, impedances, all of these three quantities will show periodic behavior, and they will repeat their value after every lambda by 2. Now, let's move on to special lengths. So I consider special loads. Now focus on special lengths of transmission line. So in this case, in our current discussion, I'm not specifying any value of L, okay? I'm just saying that there is some length of transmission line represented by L, but now I'm going to consider some specific values, okay? So now consider special lengths. So let's assume that length of transmission line is lambda by 2. So irrespective of, now I'm not specifying the load. So ZL can be any load, okay? ZL can be any load. But now I am specifying that this transmission line length is lambda by 2. Now, if ZL is not equal to Z0, so we consider this as a general case that our load is not matched. So on this transmission line, we will have incident wave as well as reflected wave. Okay, so voltages and currents they will have their general form in terms of incident and forward wave. So e power minus j beta z plus reflection coefficient e plus j beta z, and current will be v naught plus divided by z naught e power minus j beta z minus reflection coefficient e plus j beta z. So current and voltages, they can be represented by this. The interesting result that we want to look at is how much will be impedance. So if I measure impedance over here, so how much will be this value? So what is the general form of impedance equation? It is Z naught ZL plus J Z naught tangent beta L divided by Z naught plus J ZL tangent beta L. All you need to do is substitute the value of L because we are given this information. So all you need to do is replace L by, so again, because that is beta L, so beta L can be replaced by beta L means 2 pi by lambda, and then L is given to us is lambda by 2. So you will get beta L to be equal to pi, beta L equal to pi. So you get tangent 180 degree is equal to 0. So tangent of 180 is 0. So this term will cancel out, this term will cancel out, this will cancel out. So what you will get? Z in is equal to ZL. And which is a very important result in the sense that whenever you connect any general load, okay, or you can say any load, right now I'm assuming that ZL is not open circuit or short circuit, okay, which is the special case. For any load, if it is connected with a transmission line having a length equal to lambda by 2, and then if you measure the impedance, you will get the same impedance as that of the load. So in a number of situations, you want that whenever you connect a load to a transmission line, at the other end of the transmission line, the impedance should not change. So in that case, you need to make sure that you use a transmission line having length equal to lambda by 2. Now, because we are talking about periodic nature, so if you remember, I mentioned that transmission line is periodic with a period lambda by 2. Okay, so if transmission line repeat its behavior after lambda by 2, it will also repeat its behavior after 2 lambda by 2, 3 lambda by 2, 4 lambda by 2. Just like if from signal and system perspective, if you remember, when we say that if t is the time period of the signal, so 2t is also the time period, 3t is also the time period. So, but capital T is the fundamental period. So, in a similar sense, you can say that transmission line fundamental period is lambda by 2, but 2 lambda by 2, 3 lambda by 2, 4 lambda by 2, and so on. They are also the periods of transmission line. So if you connect a transmission, if you connect a load with a transmission line having length equal to lambda by 2 or 3 lambda by 2 or 4 lambda by 2, you will still get the same behavior, and that is Z in will be equal to ZL. Now let's consider another special length, and that is L is equal to lambda by 4. So I'm assuming that we are connecting a general load. So again, there will be incident wave and reflected wave, assuming that reflection coefficient is not zero. So total voltage and total current can be represented by this. But let's look at the behavior of impedance, input impedance, in which I'm more interested. So if you use this value in the expression of input impedance, or sorry, impedance equation, you will find out that Z in comes out to be equal to Z naught square divided by ZL. Z naught square by ZL. Now, what is the uniqueness of this result? So there is a transmission line. Its length has been kept lambda by 4. And irrespective of there is a general load, and then if you find out how much impedance will be there between these 2 points, it will be according to this result. So if you look at this, this Z naught is a constant. Okay, this is the characteristic impedance of the transmission line. So what is the relationship of Z in and ZL? So this is the behavior. At the input, the impedance will be equal to 1 over ZL, and 1 over ZL, you can also call it, if ZL is impedance, so 1 over ZL, we call it admittance. You can say that load impedance get transformed into load admittance. Load impedance get transformed into load admittance. This is the effect of this special length. Later on, after midterm exam, we will use this particular length for a very special application. But at this point, I'm going to give it the name that we will frequently use in this course. It's called as quarter wave transformer. It's called quarter wave transformer. So any transmission line having length equal to lambda by 4 is known as quarter wave transformer. Now, transformer word is used because of the reason that I have pointed it out, that this length of transmission line transformed load impedance into load admittance. So this is not the transformer that you people are used to in your uh, electrical engineering. This is not that transformer. It is transformer in the sense that it is transforming impedance into admittance. Okay, and I will just point out its use, but we will explore that concept in more detail later in this course. What is the use of this particular length of transmission line? It is used for impedance matching. It is used for impedance matching. Now, there is one another thing that I want to discuss, and that is right now we are talking about transmission line connected with a load. But in many applications, you may find that one transmission line is connected with another transmission line. So I will call it junction of two transmission lines. Junction of two transmission lines. So now what is the situation? We have one transmission line. Let's say its characteristic impedance is Z0. And then we have connected it with another transmission line at this point. So this is the junction. So this is transmission line number one. Okay, so if this is transmission line number one with characteristic impedance Z0, and this is the blue color one is another transmission line. So I will call it transmission line number two. And this transmission line has characteristic impedance represented by Z1. Let me select a coordinate system. So let's assume that this is the axis along which we have placed our transmission line. And again, as before, we consider this as Z. And let's denote that the point at which these two transmission lines are connected together is Z equal to 0. So it means on the right hand side, we have Z greater than 0, and on the left hand side, we have Z less than 0. In order to analyze this situation, we will assume that the transmission line number two, either it is infinite length. So transmission line number two, either having infinite length or it is terminated by matched load. So in both cases, whether we consider this possibility or this possibility, the point is that there will be no reflection from this end. Okay, there will be no reflection coming from, or there will be no reflected signal that can appear from this side. Okay, so what is the situation over here? There is a signal. Let's assume that we have connected a source somewhere over here or generator, and because of that source, a wave is produced and it starts traveling on transmission line number one. As soon as this wave reaches to that point, because Z1 and Z0, they are not equal. So what is going to happen? Some part of this signal is going to reflect back, and some part of that signal will be transmitted on transmission line number two. Okay. Now we need to find out reflection and we need to find out transmission. The reflection, how much is going to be reflection? That is going to be calculated based on this result that we have been using, Z1 minus Z0, Z1 plus Z0. In this case, this Z1 is acting as a load. Okay, Z1 is acting as a load. Just like the standard equation, let me go back. I use it somewhere here. Yes, this one. This gamma is ZL minus Z0. Now in this case, for transmission line number two is kind of a load. Transmission line number two is kind of a load that we have connected at the output of transmission line number two. Okay, so this is how the impedance at these 2 points must be equal to Z1. Okay, so gamma will be equal to this one. Okay, now let's make use of the voltage equations. So I will first of all find out what is the situation on this in this region. So in this region, you can see that we have two waves. This is incident wave and this is reflected wave. So if I want to find out the expression of voltage, so I will say for Z less than 0, total voltage total voltage must be equal to, mathematically represented as V naught plus e power minus j beta z plus reflection coefficient e plus j beta z. So you can clearly see we have this is the mathematical representation of this incident wave, and this part of the wave is the mathematical representation of this wave. So for z less than 0 region, it means this region, we have total voltage mathematically represented like this. Okay, but for this region, so now for z greater than 0, it means now I'm talking about transmission line number 2. So I will say for z greater than 0, we only have this wave. So how much is going to be the voltage, or what is the mathematical representation? So this is what we call as transmitted wave. So what is going to be the magnitude of the transmitted wave? It must be equal to the incident magnitude, which is V naught plus, multiplied with this transmission coefficient. So the transmitted wave magnitude will be equal to T into V naught plus, and this wave is traveling along positive z axis, so I will say e power minus j beta z. So I have mathematically represented the voltage on this portion, which is this one, and voltage on this portion, which is represented by this. Now, what is going to be the relationship of this voltage and this voltage at z equal to 0? They must be equal, because this voltage when equated at z equal to 0 and this voltage equated at z equal to 0, they must give us the same result. So I'm going to put z equal to 0 in this expression, and then z equal to 0 in this expression, and then I'm going to equate them together. So I will say what I'm doing, equating these voltages at z equal to 0, at z equal to 0. So what you will get from this expression at z equal to 0. So z equal to 0, this is 1, this is 1. So you get V naught plus into 1 plus gamma. V naught plus 1 plus gamma. This must be equal to, what is the result of this expression at z equal to 0? So at z equal to 0, this becomes 1, and you get T into V naught plus. You get T into V naught plus. So this will cancel out. So how much is transmission coefficient? It is equal to 1 plus reflection coefficient. And how much is reflection coefficient? Reflection coefficient is equal to this thing. So let me put this value. So 1 plus Z1 minus Z0, Z1 plus Z1, and then you can easily simplify this. So you get 2 times Z1, Z1 plus Z0, and this is the expression of the transmission coefficient. So whenever you have a connection of two transmission lines, you will have reflection as well as transmission. So if you want to find out how much is the reflection, so this is the equation that you can use to find out the amount of reflection. And if you want to find out how much is transmitted on the second transmission line, this is the equation that you people can use. Now, before I conclude this lecture, let me introduce, or I will say you people have been using it in your other courses as well, but because for microwave engineering, it's very important, and that is we normally use this dB scale, okay, in microwave engineering. So you need to be very you should be convenient or you should be comfortable in using dB scale. So one thing that people already know is that if you have two powers, let's say P1 and P2, these are two powers. So sometimes uh, rather than being interested in the actual value of P1 and P2, we are more interested in what is the ratio of these two powers. What is the ratio of two powers? And that ratio is generally expressed in dB scale. So what you do, you take the ratio P1 by P2, then you take the log of that, and then you multiply it with the 10 factor. And this will give you the ratio of P1 and P2 in dB scales. Okay, so this will give you dB. So there are some special ratios that you people must be comfortable with. If this P1, if P1 is twice of P2, okay, how much is P1? P1 is twice of P2. P1 is equal to twice of P2. If you use this result in this expression, you will get the answer 3 dB. You get the answer 3 dB. So whenever you have a ratio of two powers being expressed in 3 dB, so this gives you an indirect idea that the power P1 is twice of P2. Okay, so this is the most important dB ratio that we use in electrical engineering. But irrespective of this ratio, depending upon how much is P1 relative to P2, you will get different values in dB scale. Okay, so if it is also possible that P1 is less than P2, then this value will be negative. Okay, then this value will be negative. Okay, for example, if the ratio of P1 and P2 is minus 0.1, it means P1 is less than P2. So if you put this ratio in this expression, you will find out that you get answer minus 10 dB. So if the ratio, if dB ratio is a negative scale, it gives you an information that the power in the numerator is less than the power in the denominator. Okay, this is something that you people might have already used in your previous courses. What I am more interested in is another scale that we use, and that is known as dBm. dBm, and this M is for milli. What is this dBm? So dB scale is used for expressing the ratio. So if I know that the power, if I know that the dB in dB scale, the ratio of P1 and P2 is, let's say, 3 dB, it gives me only this information that P1 is twice of P2. But what is P2? What is the exact value of P2? We don't know. We cannot say with 100% surety that P2 is 1 watt or P2 is 3 watt. They can have any number, because if any power is twice of any other power, so there are infinite possibilities. So we cannot predict what is the absolute value of P2 and P1 if we use dB scale. But this dBm scale is different in the sense that if you know some value in dB scale, then you can directly tell how much is the absolute value of power. And how it is being done? So dBm scale, dBm is equal to 10 log of 10 and any given power P divided by 1 milliwatt. So in this case, this P2 is taken as always equal to 1 milliwatt. So 1 milliwatt is our reference. So if I want to find out the value of any P relative to 1 milliwatt, the value that you will get after using this expression will be known as dBm, will be dBm. Just to give you an idea, if you are given that the power value is 1 milliwatt. 1 milliwatt. So how much will be in dBm? In dBm, you will get 0. So if I tell you that there is there is some power and its value is 0 dBm. So now I exactly know how much is this power. How much is this power? This power must be equal to 1 milliwatt. So if you want to find out, or if you want to express any given power in dBm, you need to compare it with 1 milliwatt. So now if the power that I'm comparing is also 1 milliwatts, you get 0. And if the value of P is more than 1 milliwatts. Of course, this number will increase. Just to give you an idea, let's say if P is equal to 2 milliwatt, so in dBm scale, you will get 3 dBm. So if any power value is 3 dBm, it means the actual value, absolute value is 2 milliwatt. Now there is no confusion. Previously, when I was telling that the ratio of two powers is 3 dB, I cannot tell what is P2 and P1. But now if I give you this information that the power is 3 dBm, then I can exactly tell that power is 2 milliwatt. So you should be very much comfortable with this dBm scale in as a electrical and especially as a microwave or communication engineer. Okay, so that's it, and this is the final lecture before midterm exam. Thank you very much.